This video will be going over section 4.6, which is on exponential and logarithmic equations. The topics in here. The first thing I'll introduce is something that's a little new as far as formulas go, as far as properties go. They are called the one-to-one properties of logarithms and exponents. You can already see them on the screen here. And then we'll just look at solving some exponential equations, what the method is, what some things to look out for, and what things you're allowed to do. And then we'll look at solving some logarithmic equations. So the one-to-one properties of logarithms and exponents I have highlighted here. I'm going to go ahead and scroll down very quickly to an example of a problem, just so you know what an exponential and logarithmic equation is. So this is an example of an exponential equation. Both of these are, because what we're solving for is in the exponent. And this looks a little different. We'll get down to number 4 and 5 and talk more specifically about those, but these are logarithmic equations. They are equations where the thing we are solving for is inside the logarithm. So what we're going to do is first kind of look at these one-to-one properties, what they say. These are just useful tools. They will oftentimes, not often I guess, but sometimes the problems are written in such a way that if you can use these one-to-one properties, it just saves you quite a bit of time. The first one, the exponential one-to-one property, it says if you have a to the x equals a to the y, that is the same as saying x equals y. Now the way you want to interpret this is if you have exponents on each side with the same base, that's why they're both a. If you have the same base, then you can pretty much cancel the base out. You set the exponents equal. And that's because the exponential function is 1 to 1. Passes the horizontal and vertical line test. All right. Logarithmic graphs are the same. You can think about the shape. It's going to pass the horizontal line test. We have log base b of x equals log base b of y. Once again, same base. But if you have the same base of log on each side, then you can set the end sides equal. But one thing I like to mention here that I have written at the end of these is you only have one on each side, one exponent. You just have something raised to a power on each side. The base is the same. In this one, you have to have only one log on each side, nothing outside of it. Everything has to be inside, and they have to have the same base. All right, but we'll look at solving exponential equations first. These are definitely the more common of the two types as well, which we'll see in the next section when we do word problems. An exponential equation, like I said, is an equation which the variable you want to solve for is in the exponent of an expression or an equation. The general strategy to solving an exponential equation is to isolate the exponential part. And I'll talk about what that means when we get down to the problem. But you want to isolate, which means get the exponential part by itself and then switch to log form. But the other option you have here is using the one-to-one property. But it would still be based around doing the same idea, isolating the exponential part. If you're trying to get the exponential part by itself, then really that takes on the same form here, a to the x by itself. And number 4 and 5, when we get there, this is what this warning is for, which I'll talk about. But whenever you have something that looks a little bit different exponents, exponentials mixed with like x and x squared, you can think about factoring those as well. You're allowed to factor when you have exponential things, which we'll see. And so the first one here, what we're going to do in all of these problems is give exact answers, meaning not type in our calculator, do the whole thing out, get x equals or n equals for this first one. And if it's kind of a weird number and we'd like to approximate it with a decimal, we'll type in our calculator and do that as well. So number 1, we want to solve 5 times 3 to the n power plus 38 equals 443. Now, we talked at the beginning of this chapter, something like this, you cannot interact the 5 and the 3. One's raised to the n power, one is not. But what I'm referring to when I say the exponential part is this, the part with the base with the exponent in it. Why my mouse is being a little fidgety right now. I can't write precisely. And so this is the exponential part. This is what we want to get by itself. Okay, so we want to get this by itself. You can kind of think about this thing as being x in the sense of how you solve it. If you had 5x plus 38 equals 443, we would subtract the 38 off to get that away and then divide by the 5. The idea is exactly the same. Kind of think about how you would solve it for x, but realize you're going to have one or two more steps at the end. So I'm just going to start by rewriting it. That way I can do my work underneath. I start, like I said, subtracting the 38 on each side. I'm trying to get that 3 to the n by itself. The first step is to get the term that it is in isolated. So what we're left on the left side is 5 times 3 to the n power. And on the right side, 443 minus 38 is 405. Then divide by the 5 on each side, right? Just remember, if you think about this exponential part as x, it's like having 5x. You would divide by 5 to get x by itself. And we're left with, on the left side now, we have the exponential part isolated. It's 3 to the n. Because everything else is gone from 3 to the n, if you don't want to write the parentheses anymore, you don't have to. If you want to leave it there, you can. And 405 divided by 5 is 81. All right, so once you're at this step, you can do the problem one of two ways. Some of these problems work perfectly in that solving 3 to the n equals 81. 81 is a power of 3, and you can use the one-to-one property. Since this is really the only one we have in this problem set like that, I'm going to go ahead and do it that way. And you'll see with the other ways how you would do it if you didn't have similar bases. But one thing you want to notice is 81 is a power of 3. In fact, it is 3 to the 4th power. So we can write it with the same base on each side. We go ahead and plug it in just so you can see how this one-to-one property works. We got 3 to the n equals 3 to the 4. And we can use the one-to-one property because the one-to-one property says, I'll scroll up and remind you, if you have exponents on the same side, exponential things on the same side with the same base, you can set the exponents equal. We can knock out the 3 and we get n equals 4. And that is our answer. That is our one-to-one property. All right, now this one, since our answer is nice, it's just 4, that there's no decimal approximation there, that is it. So that's why I have the when appropriate written in. All right, but that's one kind of problem. Always, whenever you have just one x or one n, x in the next one, you want to think about getting the exponential part by itself. Really, the only thing that changes once you do that at this step, your problems can branch off one or two ways. So number 2, same deal. We want to solve e to the 3x plus 3 equals 53. It is an exponential equation because x is in the exponent. And you also want to realize that the exponential part's already by itself. The fact that there's 3x plus 3 in the exponent's not important. It's one exponent, 3x plus 3, and the x is in there. The exponential part is by itself already. The exponential part is by itself. What that means, you kind of think about being here already. If you can write the two sides as exponents with the same base, you want to do that. But you cannot write 53 as a power of e, at least easily. And in this case, we are going to switch to log form. That's the other option. Okay, so since 53 is not a nice power of e, it's a power, it's something, but it's not going to be a nice one. What we want to do is we want to switch to log form instead. And this is something we did at the beginning, sort of at the beginning of this chapter when we started talking about logs. I'm going to rewrite the equation and just remind you the method. This is the thing where you grab the base and move it to the other side. If you want to go from exponential form to log form, we grab the base, which is e, and we move it to the other side. Remember, when we move the base to the other side, what remains is the exponent here, which is 3x plus 3. And we get a log with its base being our original base over here, e. And what goes inside is the number over here. Now, I can't stress this enough. Many people do not write parentheses around what goes inside the log, and when you go through the next steps of this problem, it can cause confusion. I really just can't stress enough. Write these parentheses around here. What this is going to tell you is that 53 is going to be inside the log and nothing else because it's closed off. Okay, so while it's not a necessary thing, I really can't not stress it enough. Let's go ahead and just write that in. Right. Now, before I finish solving this, I'm going to switch log base e to the natural log. Yeah, what you'll find in most problems we have, the base is e with exponential equations. That's because that's what happens when you do word problems. The base is almost always e. And you kind of want to get used to switching to log form means, you know, the log that's going to pop out on this side is the natural log, because that's what log base e is. But now you want to finish solving for x. This is not something to be afraid of. This is just some number. If you had 2 over here, if you had to solve 3x plus 3 equals 2, you would know exactly what to do. You would subtract the 3 and then divide by the 3. We're going to do the same thing. You want to get 3 by itself, subtract 3 on each side. And this is where it's really important to have the parentheses around, because the minus 3 doesn't go to the 53 because the 53 is inside the natural log. It goes outside of it. And I just like to put it behind. You can put it in front. Minus 3 plus the natural log of 53 works as well. And to finish up, going from 3x to just x, we divide by 3. And we get x equals the natural log of 53 minus 3 in the numerator, and the whole thing is divided by 3. And you can't cancel these 3's out because of the minus here. So this is your final exact answer. This is what we mean by exact, is we didn't do anything in the calculator. There's no decimals. Now, if we want to get the approximate answer, which for this problem we want both, you want to type it in the calculator. So I'm going to go ahead and do that and pause. So go ahead and type this into our calculator. Natural log of 53 minus 3, and then divide the whole thing by 3. And like I always say with the calculator, just do as much as you're comfortable with. You can type in the whole thing at once. I like to do the numerator by itself. So I got natural log of 53 minus 3. Make sure you type it in with those parentheses and everything. Hit enter. And then we want to divide by 3. We get 0.3234 rounded to 4 spots. All right, so most problems ask for both. You want to make sure you can type in your answer correctly in the calculator, but also that you're not just using the calculator to get the final answer here. Now you can check your answer. It's a lot easier to check with the approximate answer. What I will do is just take the left side here, e to the 3x plus 3, and plug in 0.3234 to see if it's about 53. So we got the e raised to button is right here. You can also hit the e right here and do the caret. But we got e raised to the 3 times 0.3234 plus 3. And you can see, because we did round, it's not perfect, but it's very close to 53, so we're good to go. All right, next one's rather similar in style. It's kind of a combination of number 1 and 2. Number 1, we talked about isolating the exponential part, which is what we have to do here. But because of the e, we're going to have to do the approximate and exact thing. All right, so we want to get this by itself. We want to isolate the e to the x, the exponential part, by itself, like we did with number 1. Right, now, once again, just think about this. If this was x, we would add 8 to each side, get the part with x by itself. We got 12 times e to the x equals 9 plus 8 is 17. And then divide each side by 12 to get to e to the x part by itself, the exponential part. We got e to the x equals 17 over 12. Now, once again, just like last time, it's not really possible to write any number written like this as a power of e very easily. So we switch to log form. We take our base and we move it to the other side to get x. Right, that's our only way to get x out of the exponent. Right, and on the left side now we got just x, and on the right side we got log base e, which remember is ln. The important thing is you want to make sure you put the entire side, the entire fraction inside 17 over 12. You don't just put the 17 in there and divide it by 12. You have to put the entire side. Whatever is on that right side when you switch to log form, every time is going to go inside the log. It doesn't matter how messy it might look. Right, but what we see here, this is solved for x. We have x equals. This is our exact solution. Just like last time, we didn't do anything with a calculator. We got x by itself. And you wouldn't want to do anything to try to switch this. once you get the exact solutions on these, don't think about trying to do log rules maybe to write it a different way. 1 log is almost always the simplified version. So it's our exact solution. If we want the approximate solution, we type that in our calculator. And natural log of 17/12. Hit the natural log button. Make sure you put 17/12 all inside there. And we get 0.3483. So once again, most of them ask for both if it's applicable. Some of them, when they only ask for the answer, it's kind of an exact answer. It's kind of an indication that you're going to be able to do it like number 1. But just beware. You need to know and understand the difference. All right, so number 4 and 5 are the problems where they look a lot more complicated. But if you realize one thing, which I'm going to show you, you can factor with these things. They can all be factored. All right, so I'm just going to go ahead and point that out about these two. Is here you see the number 5 here. When we get there, you see the different powers. You cannot combine these because they are different powers. And on number 4 here, we have x's and x squareds with stuff. You want to think about factoring these. Now, you can factor e to the x or 2 to the x, any exponential, just the same way you would factor x squareds and x's and stuff like that. And so the first thing you want to do for number 4 here is notice that there's an e to the x in common with every term. It's already set equal to 0, so we can begin factoring it. And when you have something in common, when you're factoring, you factor out the greatest common factor. Which is our e to the x. So we factor out e to the x, and on the inside what we're left with is x squared minus 3x minus 10. Right? It's just like if you were factoring out an x in common. If you had like x cubed minus 3x squared minus 10x. You would take that x out and you'd be left with whatever's inside. All right, now once we factor that, I like to just try to factor everything that I can and then solve it. So the question is, can you factor x squared minus 3x minus 10? And the answer is yes. So we just keep on factoring. We have our e to the x outside, just leave that alone. And the x squared minus 3x minus 10, that factors to x minus 5 times x plus 2. And that still equals 0. And so once again, remember 0 has to be on one side in order to factor it. This one's already written like that. That's something to be aware of. Right, but your method of factoring never changes. It doesn't matter what's inside here. We can have e to the x. We can have a whole bunch of different kinds of things. Once you factor it, set each factor to 0. All right, we did this a lot last chapter. We didn't have any e to the x's, so it kind of looks weird, but we set the e to the x equals 0, we set the x minus 5 equals 0, and we set the x plus 2 equals 0. All right, now the one in the middle and the one on the right were probably more quick to solve those. We get x equals 5 for the middle one, we add the 5 to each side, and x equals negative 2 on the right one, subtract the 2 from each side. What you want to notice about the one on the left here is that it's an exponential equation with the exponential isolated, and you can already just switch to log form because the exponential part's by itself. Right, so it's sort of like this problem here, just with 0 on this side. Okay, so we switch to log form. And when we do that, we get x on the left side equals log base e, which is natural log of 0. Now, one thing you want to be careful on is remember the domain of logarithms. The inside must be a positive number. And 0 is not a positive number. I'll show you in the calculator just to remind you can use that. But this is not a solution. This is D and E, at least for this part, because natural log of 0 is not a real number. So natural log of 0, you can see that. Never happens. So we do have two answers. Don't write D and E in the problem. Our two answers are 5 and -2. Okay, 5 and -2. These are already nice numbers like the first one we did today. You don't have anything to type in your calculator. That's it. All right, so that's one common kind of equation that pops out when you are in a calculus class. Another one is something like this. Sorry, I didn't mean to hit the mouse the wrong way. It's us solve e to the 2x minus 3e to the x minus 40 equals 0. Now, I did mention that you will be able to factor these, and that's true, but I think this one is not anywhere near as clear. Maybe if I told you to factor this one, you would have just realized that e to the x is in common and I can take it out, and maybe after doing that you would have seen what to do. This one, if you've never been exposed to it, what you have to do is realize we have different powers. You cannot combine. Just like you can't combine x and x squared, you cannot combine e to the 2x and e to the x. But what you want to do is kind of think of e to the 2x in a different way, using an exponent rule. E to the 2x, we usually do this the other way, but this is the same thing as e to the x squared. Right, we're used to thinking about this from the right to the left. If we want to simplify the exponent, the way we would combine these is to multiply to get to 2x. All I'm going to do here to start is just plug this in for e to the 2x. So we got e to the x squared minus 3 times e to the x minus 40 equals 0. Now, why does that help us out so much? The important thing to notice here, and I'll do a little substitution, this part you don't have to do on your own, but it's helpful when you see it for the first time. If we kind of think about e to the x as like a y or something, meant to write u's. For some reason, start with an L. So use y equals e to the x. Okay, so everywhere in this equation that I see e to the x, I'm going to put y. Get y squared minus 3y minus 40 equals 0. Right, this is something that you're very familiar factoring with. At this point, you probably see how to factor it, hopefully. This factors to y minus 8 and y plus 5. Right. And what I'll do is I'll finish this, solving this, which is we can do very quickly, and then what you have to remember is to plug back in. So we set each one to 0, and we get y equals 8 and y equals negative 5. The very, very, very important thing to remember is that you are solving for x. X is what our original variable was. You must plug back in, and I like to plug back in here. So we're going to now plug back in e to the x for y and solve for y. Or sorry, solve for x. All right, so we've got e to the x equals 8. And e to the x equals negative 5. Do not want that looking like a negative. Right. Now once you're here, you have to solve each of these, and this is one that we pretty much worked in every problem since number 2 on this. Right, all we do is switch to log form. And we know e to the x, when we switch log form, we get the natural log of the other side, when we got to do it for both of them. So we switch log form on each of these. The one on the left, we get x equals the natural log of 8. And the one on the right, we get x equals the natural log of negative 5. Now, if you remember what we did last time, we wanted to make sure our answers work. Anytime you do some sort of factoring, it's possible that you get answers that don't work. I mean, even in these problems, if you ended up with a negative number here, you would have no solution. So just type both these in your calculator, confirm. This one should be fine because the inside's positive. This one should be wrong. This should not be a real answer because it's negative. Okay, so we do ln of 8. Now we get 2.0794. So this one's fine. And the one on the right, the natural log of negative 5. And we should not get a real answer, and we do not because of the negative inside. But we are not going to use this. This one, for lack of a better term, this one has no solutions. All right, but after solving this one, we have one answer. This is the exact answer, natural log of 8. And the approximate solution we got when we typed it in our calculator, 2.0794. Right. But as far as exponential equations go, that's the overall approach. I will remind you, just on the first one, you can see that one-to-one property used. It is a good idea to practice it. But this is also something, if you switch to log form and you typed what you got, when you switch to log form, you would still get 4. There would be no issues there. Right, but the one-to-one properties can definitely save time. Right, logarithmic equations are a little bit different. Their answers typically look more nice, because when you're solving a log equation, you switch to exponential form. And when you switch to exponential form, the log is gone. So the log's not really in your answer, but there is one issue with solving log equations. And all of our log rules only work if the inside's positive, because that's the domain. So if we solve this thing here, when we get to it, we would have to make sure that our answer is actually our answer. And what you do there, anytime you solve a log equation, there are some times when you don't have to check your answer by plugging in, but I feel like it's just a good habit to plug in and check your answer anytime you solve a log equation, because you might get extra answers that aren't really answers. But the general approach to solving a log equation, we are going to get the log on one side and switch to exponential form. Or you can get a single log on each side and use those one-to-one properties. So I'll just scroll down to show you where we would use a one-to-one property. We will end up using one here because there's logs on both sides. So when we get down to there, we will use a one-to-one property. Right, but we'll go ahead and fire through these. The first few aren't bad at all. The first one we want to solve for x, log base 3 of x equals 4. And what you want to know is the log part is already isolated here. We can directly switch to exponential form. When it comes to using the one-to-one properties here, you only use it if you already have logs on both sides. If not, you always just switch to exponential form. Your answer can still be nice both ways. All right, so I'm going to just rewrite it and do the one step here. We grab our base when we switch to exponential form and move it to the other side. Remember, the log goes away. What's left inside on the left side is just x, whatever's inside, and the right is 3 to the 4 power. And 3 to the 4 power is 81. That is our answer. It is just 81. All right, now, like I said here, anytime you solve a log equation that starts with more than one logarithm, you must check your answer. This one's going to work, but just so you can see that it works, you can check by plugging it into the original. You have to plug it into the original when you check. That's why I have the original part bolded and capitalized. You must check in the original. Okay, so does log base 3 of 81 actually equal 4? Okay, we'll go ahead and look. Log base 3 of 81, I'll remind you, change of base. This is the same thing as ln of 81 over ln of 4, unless your calculator has the change of base in it already. You can type this in. Is ln of 81 divided by ln of 3 equal to 4? And it is, so it works out. When it doesn't work, which we'll see examples of later, it'll spit out an error, because what's going to happen is you're going to have a negative number or 0 inside the logs. Yeah, so the next one is just building on it. It doesn't have the log isolated by itself, but you want to do the same thing you did with exponential stuff. You want to isolate the log part. So we want to get this by itself. We subtract the 9 from each side. We got 8 times log base 8 of x equals 16 minus 9 is 7. Now what you do here is very important, because we do have a log rule about moving the 8 up as the exponent. But you don't want to do that. That makes the answer more complicated. What you want to do is divide each side by 8. If you want to get the log by itself, the easier thing to do is divide by the 8. Right, it is definitely 100% easier to do it this way. We got log base 8 of x equals 7/8. Now that we've gotten the log part by itself, we switch to exponential form just like last time. And we get x equals, it looks kind of funny because the 7/8 has to go in the exponent. It's 8 to the 7/8 power. If you are looking for the exact answer, this is it. You can type this in your calculator, which we'll see, and it's going to be a messy decimal. This is the exact answer. Right? Because remember, anytime we have a fraction, it's really a radical. Now, if we do type this in our calculator to get the approximate 8 to the 7/8, and just look out for the directions, which one you want. You might want both. 8 raised to the 7 divided by 8 power. We get 6.1688. Okay, either one works. Since there is only one log in the original problem, you're good to go. You can check your answer. But the only one log means this is going to be our correct answer. But I do encourage you to check if you don't feel confident, or one thing is if you don't get the problem right on a problem like this, check by plugging in and see, do I get close to 16? You may have just made a quick mistake here. You may have even typed this in your calculator wrong and you have the right answer here but not here. All right, but we don't need to check this one. All right, number 3 is much the same. Right, we don't have just x inside the log, but that is okay. It's just like the problems before, when we didn't have x inside the exponent, you still get the log part by itself. Right, you have no log rules to simplify this. That was one of the big takeaways from the last section. So it's got to be stuck together. But we do the same thing we did with the previous problem. We want to get this by itself and then switch the exponential part. All right, so we would start by dividing each side by the 4. Get rid of that 4. And we get the natural log of 7x plus 3 equals 3/4. Separate those two problems. Just like with the last section with exponential stuff, when you solve log equations, it's probably going to be most likely you're solving one with a natural log, because that's what happens in applications, is base e. But we want to switch to exponential form now. We grab our base e and we move it to the other side. We're switching, and we get 7x plus 3. The inside equals e to the 3/4 power. Okay. We get e to the 3/4 power. Then to finish it up, right, one thing I want to remind you again is this is just a number. We're going to leave it alone. We subtract the 3 from each side. We get 7x equals, right, the exponent here, this is not going in the exponent, it's going off to the side. So I got e to the 3/4 minus 3. And then we divide each side by 7 to get x by itself. And we get x equals e to the 3/4 minus 3 in the numerator over 7 in the denominator. That is our exact answer. It's very, very messy looking, but that's just the exact answer. If you want the exact answer, that is it. if you want the approximate answer, we would plug it in our calculator. Okay, so we got e to the 3/4 minus 3 in the numerator and 7 in the denominator. All right, if you hit this e to the x button, we'll get e when we put our 3/4 in the exponent. And we got minus 3. E to the 3/4 minus 3 in our numerator. And then divide by 7. We get negative 0.1261. Oops. Now, one thing that could pop into your head is we're not supposed to have negative answers. Well, you can have negative answers. Yeah, they just can't be negative when you plug in here. So this, I will guarantee, I'll plug it into the original just to show you, but it is guaranteed to work because we only had one log. Right, so if you don't feel confident in your answer, once again, if you just want to check them all, there's not an insane amount of problems here in this section, at least as far as log equations go. Go ahead and check them. Is 4 times the natural log of 7 times our answer, negative 0. That's a little dyslexia. Negative 0.0. Jeez. Negative 0.1261. Plugging in for x plus 3. Right, you must check in the original. Does that equal about 3? So I'm going to type that in. 4 times the natural log of 7 times, what was our answer? That's right here, so I can use that. Negative 0.1261. And then I forgot what else was in there. Plus 3. Question is, does that equal about 3? And it does. We rounded, so it's going to be a little off, but it's about 3. It works. All right, your answers can be negative. They can be positive in log equations, because what this is doing is changing your domain, and this happens to be in the domain. Got a couple more problems left. Number 4, we are trying to solve log of x minus 2 minus log of 1 minus x equals 1. And the thing you have to notice here that's very different from the other ones, just remind you very quickly, all of these had one logarithm in them, and this has 2. And a good thing to keep in mind when you're solving any log equations, if you have more than one log on one side, you want to combine them into one. In order to either use the one-to-one property or switch to exponential form, you need to combine logs into one. We want to combine these into one to start. And do remember the rules here. We have 1 as our coefficients. We can combine them directly. And subtraction on the outside becomes division on the inside. We get log of x minus 2 divided by 1 minus x. And that equals 1, because all we did was change this side. We combined this into one log. But once you're here, you can switch to exponential form because you have one log over here. Even though the inside's messy, it's one log. And we're going to switch by grabbing the base and moving it like we always do. So we switch to exponential form. On the left side, we are left with what's inside x minus 2 over 1 minus x. And the right side, we have 10 to the first power. All right, and I'm just going to write real quickly change that 10 to the first, get rid of the first power because it's the same thing as 10 before we go to the next step. Right, but we've gotten rid of the log. We are now at an equation that you know very well how to solve. Whenever you're solving an equation with a fraction, one of the first things, if not the very first thing you want to do, is get rid of the fraction. And for something like this, you can even think of cross multiplication. Think about the 10 being 10 over 1. We can cross multiply. That's one way to think about this one. But you want to get rid of the fraction. So we got 1 times x minus 2, which is x minus 2 on the left. And on the right, we got 10 times 1 minus x. Right, and from here, just continue solving it. Now you've gotten rid of the fraction. You can distribute your 10 through. We get x minus 2 equals 10 minus 10x. And just continue solving. I'll add the 10x to each side to get the x's on the left. And I'll add the 2 on each side to get the x's isolated. So the 2's are going to cancel, the 10x's are going to cancel. On the left side, x plus 10x is 11x. And on the right side, 10 plus 2 is 12. Going to need this original to check our answer, so I don't want to scroll down anymore. All right, divide each side by 11, and we got x equals 12 over 11. Right, one thing you want to also realize that's different from this one, it's kind of what we pointed out before, is that there's more than one log. You do have to check your answer. And you need to check it in the original like we talked about before. Okay, so we have more than one log in the original. We must check. And you must check in the original equation. You cannot check after you've done anything. If you checked it right here, it would probably work every single time, but it's not going to necessarily work every single time. All right, so let's go ahead and check. We got log of 12 over 11 minus 2. Right, plugging in x is 12 over 11 into our equation. Minus log of 1 minus 12 over 11. And the question is, does this equal 1? All right, you can do this one of two ways. You can type this in your calculator, see what it gives you, or you can see, are the numbers inside positive? But I'll just do it in the calculator. Okay, so that one was log, that's what we have a button for. We had log of 12 divided by 11 minus 2. And that was the first part. And then we're going to minus log of 1 minus 12 over 11. Right, it's pretty lengthy to type in the whole thing, but you do want to just type in the whole thing and hit enter. If you hit enter, you should see an error because 12 over 11 gives negative numbers here. 12 over 11 minus 2 is negative. 1 minus 12 over 11 is also negative. So this is not a solution. 12 over 11. But what we found here is that it's the only possible solution. And since it didn't work, there is actually no solutions to this question. So you put D and E for this one. Okay, so there happens to be no solutions for this one. There might be one, there might be none. Pretty much with any of these log problems, once you combine them, you have the opportunity to make extra solutions. They might all work, they might not all work, none of them might work. Just depends. Right, number 5 is a similar idea, except this is one that we're going to use the one-to-one property on. I want to make sure we did one of those. But the first thing you want to talk about, address, is right here. You want only one log on each side. So we got to combine these into one, just like we did the last one. And we know how to combine these. This also has coefficients of 1 in each spot. So we have addition becomes multiplication. We have ln of x times x minus 5 equals ln of 4x. All right, we didn't change this side. There's nothing to combine over here. I'd go ahead, just me personally, I would go ahead and just distribute this and simplify it. Ln of x squared minus 5x equals ln of 4x. Right. And once you're here, this is what you have to realize is you need to use the one-to-one property here. The reason is you have a log on both sides. It's the natural log, but it's still some log, and it has the same base. So one log on both sides has the same base, and there's nothing outside of the log. Right, everything that's on each side of the log is actually in it. All right, so the one-to-one property basically says we can cancel out the logs. That's what it is. And we got x squared minus 5x equals 4x. And now we can solve this. Right, different powers of x mean you're going to get everything to one side and factor or use the quadratic formula. Right, most might factor, but not all of them are guaranteed to factor. So you might have to sometimes use the quadratic formula. In order to do either of those things, you must make one side 0. Let's go ahead and subtract 4x. And we got x squared minus 9x equals 0. This one is nice because you can just factor out the x that's in common. And we get x minus 9 times x. All right, take out the x in common. And then set each factor to 0. We've solved this a lot at this point of the class. We get x equals 0 from the what's out front, and we get x equals 9 from what's inside. But once again, this is like the last one. You have to check your answers because we started with more than one log. Right, they're not both guaranteed to work. They could both work. One might work. 0 might work. It just depends. But we've got to check. And you got to check it in the original like before. Don't check it otherwise. Okay, so we'll plug in x equals 0 and see if this works. We get the ln of 0 plus ln of negative 5 equals ln of 0. Right? If we plug in 0, that's what it looks like. And this right away, you don't even need to put in your calculator. You can, but this is definitely not going to work because we cannot have 0 inside. We cannot have negatives inside if one of these is bad. You know, the inside must be positive. If one of the insides is not positive, you are done. So x equals 0 is not a solution. Then we also need to check x equals 9. Whether the other one works has no bearing. So we plug in 9 to our original equation. We get the natural log of 9 plus the natural log of 9 minus 5 is 4 equals the natural log. 4 times 9 is 36. And this is also one you can do by hand. Everything is positive here. They're all positive. And is it true that the natural log of 9 plus the natural log of 4 equals natural log of 36? Yes, it is true, because when we multiply to combine to 1, we get 36 inside. So they're all positive, and both sides are actually equal. That means 9 is an answer, and 0 is not. All right, but this just happens to be one where we have one solution out of a possible 2. What you would write in the homework is just x equals 9, or 9, however it wants you to present the solution. Right, the last one looks kind of different, but I think it's something we can definitely solve. Here, what we're solving for is in the base. We want to solve log base x of 64 equals 2. Now, the way you would begin to solve this one, you don't start it different at all. We have the log by itself. We switch to exponential form. Right? Anytime you solve a log equation, you're trying to get rid of the log, and the only way to do that is to switch to exponential form. We grab our x here, our base, and we move it to the other side. It becomes the base of the exponent. We got 64 on the left equals x to the second power on the right. And now this is something you know how to solve. We want to solve this equation. To solve for x squared, we do the square root of each side. Don't forget, with square roots, we get plus or minus. And the square root and the x, the squared part on the x cancel. We get x equals plus or minus the square root of 64 is 8. Right, so what I want to point out here, we haven't done one with solving for the base. There's only 1 or 2 on the homework, and they're both like this. But we have 2 solutions possible. We have 8 and negative 8. Right. And what you have to remember about the base here is the base has to be positive. The base cannot be negative, and it also cannot equal 1. All right, so base must be positive and not equal to 1. So if you look at our 2 choices here, x is solving for the base. 8 is certainly fine. It's positive. It does not equal 1. But negative 8 is negative. So negative 8 is not actually an answer. We only have one solution, which is 8. Right, but as far as solving for the base, that's the only kind. There's not going to be multiple logs or anything like that when you're solving for the base. It's just one of those things to remind you the base can't be anything you want it to be. But that concludes this section on solving log and exponential equations.